Hi, Kevik here. Yesterday I saw a nice video of Scott Manley. He showed me how to do simple orbital calculations. Um, he did it by hand, but I'm a software developer. I don't like doing math by hand, and as an open source developer, I don't use commercial software, so I thought, well, maybe I write my own and do the same calculations. And I'm gonna show you how you can do it. Uh, it's it's not very complicated. I'm not sure how exact the results are gonna be because sorry, I had to adjust my headphones because this deals with very large numbers, and for simplicity we're just gonna do it in JavaScript. So the I'm gonna put the link to Scott's video in the description so you can actually watch it. Maybe you should even watch it before continuing to watch my video if you haven't seen Scott's explanation of the math already. So let's start. Um, let's call this Scott Calc 1 HTML. I'm using the editor Vim here on Linux, but you can use anything you like as long as it's a text editor and not a word processor. So you can use like Notepad on Windows if you want, or Emacs or whatever. Just don't use Microsoft Word or OpenOffice or something, because that will try to insert formatting and save it as a binary file, and you might not want that with program code. So first we give it a title. Let's call it Scott Manley Orbital Calculations Part 1, because I'm doing essentially the same thing in software that he demonstrated by doing the math by hand. So, I'm also gonna include Jquery. This makes it easier to work with web forms and insert HTML text into div tags, and that you can do it without, but I've been using Jquery for years now, and I'm so used to it that I'm not sure I know how to do it without Jquery. I have to Google it. But Jquery makes other things easier also. So if you work with HTML, you definitely should take a look. So, well, we use a very modern JavaScript library. I think we're gonna do the rest a bit old school and use tables, because it doesn't have to be nice, it just has to work more or less. The first thing we wanna use the correct tag. The first thing we wanna do is we take two orbits. The user gives us two orbits, and we're calculating the transfer orbit. I think it's a Hohmann transfer orbit. If not, then I messed up, but I think it's a Hohmann transfer orbit what we're calculating. And then we calculate the delta V required on the two burns to get us into the new orbit. So first we have two rows, so let's say current orbit above surface. Many tools and games give you the current orbital distance above the surface of the planet or moon you're orbiting, but we need for the calculations the distance from the center of in this case we're doing the Earth, so we need the distance from the center of the Earth. We're also letting the user input the orbital parameters in kilometers, so we have to do some math afterwards to get the required meters above the center of the planet, and let the user input the more simpler parameters, kilometers above the surface. Input type text, ID is pair for current periapsis, value is 300. We're putting in default parameters just so it makes easier to test everything. So we don't have to input all the orbital parameters every time we try out and see if it works. Our start orbit will be simply a 300 kilometer circular orbit. And let's see, let's make our destination orbit a circular orbit, a circular geostationary orbit. New so let's see if I'm not mistaken, geostationary is, I have a cheat sheet here, so 35786. Okay, then we need a button to trigger the calculation. Let's say call span is 3, align is center, just put the button in the center, input type is button. It needs a label. This is value in HTML, so let's call it or make it go. And we need to call on a JavaScript, let's say return calc burns. and then we need some table rows to output our calculations. Let's see. We also want to output some intermediate values, just so we can check if you make an error, so we can check which values went wrong. So okay, today let's say semi-major axis. The first thing we have to calculate are the semi-major axes or axis, or however that's called. So we just want to output them. Diff ID is semi. Okay. Well, what am I doing? So this would be a diff, and this would be a TD. So we do the same for the new orbit. We also want to output the transfer orbit parameters, which is periapsis and apoapsis, which we call, let's see, whole pair, and what am I doing, and whole up. Also, and that's the main goal, we want to output our 2 burns. We need 2 burns to do a successful orbit transfer from one orbit to another, in this case. So transfer burns delta V, which, well, we burn 1, 2. Of course, the transfer orbit is in kilometer, and the delta V should be in meter per second. So I can just reuse this. We want also to output the some stats. In this case we only have one, so it's the total delta V. Delta V. We don't need this, but we just leave an empty element, so we don't have default rendering of the browser, because sometimes they make it look extra stupid. So okay, then we close the body, we close HTML. Now we can take a look at our form. This was code card 1, yes. Let's see. Okay, looks acceptable. Now we have to actually write the script. Say function calc burns return false suck. So first thing we need two variables. The first is just so we don't have magic numbers all over the place. Kilometer, 1 kilometer is 1000 meters. So when we multiply, we have just a nice named variable instead of some strange number. This also means you could theoretically change this and use something like miles in the output. Yeah, maybe you need another conversion as well, but I don't know. I use metric. Okay. For internal calculations, as we said, we need meters above the center of the Earth. So we need to know how big the Earth is. And if I did Google correctly, that would be 6,371 kilometers. Now we read the values from the web form. The current periapsis is C .val, and just we don't really check the arguments that the user puts into the fields, but we make sure we convert it to a number, multiply it so we get meters, and add the Earth radius. We need to do this for the other 4 inputs as well. And the apoapsis. Okay. Let's comment. Okay, these are magic numbers. Okay, we need 1 kilometer is 1000 meter. Earth radius at equator in meters. Then we need some other magic numbers. That would be the Earth mass in kilograms. That would be 5.97219 multiplied by 10 to the power of 24. Earth mass in kilogram, and we have G is 6.67384 multiplied by, that should be power, of course, multiplied by 10 to the power of minus 11, which is the gravity constant that, according to to current knowledge, should be constant throughout the universe. We'll see in 1,000 years or so if it holds up, but well. So, what am I doing? So, let's see. First of all, we said we need to calculate the semi-major axes. Okay. Yes, okay, var semi is what was it Scott said? Okay, yeah, of course. Current periapsis plus current apoapsis divided by 2. So we just take the what's the middle? What's the word? Whatever. And we need to do the same for the new orbit. So, and we also want to display it. Okay, semi so okay. Not. Let's try it out. I just reload, make it go, and it doesn't go. So calc burn is not defined. It should be calc burns. Okay. What could possibly go wrong? So, zack, zack. Okay. Pretty sure that means something to someone, but yeah. Okay. Calculate semi-major axis. Now we want to calculate the missing data for the transfer orbit. Basically, the periapsis of the transfer orbit is the periapsis of the current orbit, and the apoapsis of the transfer orbit is the periapsis of the new orbit. We could use that variables, but just for clarity, we define that here, so we hopefully get it right. So periapsis, and it makes the code a bit more readable if you have to go in a few months later. So the human periapsis is the current periapsis because we want to burn at the lowest point. This of course assumes you want to go to a higher orbit. If you want to go to a lower orbit, you would change that a bit around, so you get a more optimized transfer. And the apoapsis is the new periapsis. So, and the semi-major axis is same as before, ho per plus ho up divided by 2. And we use that just to check our initial calculations with converting the numbers are correct, or at least we can solve it backwards. So HTML is, let's see, we need the periapsis minus the Earth radius and turn it back into kilometers. Same for the apoapsis. Okay, let's try that out. Make it go, and nothing. Okay, did I? I did mess that up, didn't I? Let's not downloads. Hooper has no method HTML. It doesn't, does it? Why? Div ID. I should actually use the $sign so it calls actually Jquery. So yeah, and we already messed up our calculations because that would be we should use the correct parameters. Yes. Now that looks a bit more reasonable, I think. New pair up pair, yes, okay. We are already at the point where we can calculate a first burn. That's that very complicated formula. Calculate first burn. What we need is our current speed at periapsis and the speed we need at periapsis for the transfer orbit. So first thing is periapsis speed is, let's see, mu. We didn't define mu. Okay. Mu is just mass multiplied by gravity constant. So let's see, mu by 2 divided by current periapsis minus 1 divided by per semi, and we need to take the square root of this, and there's still one problem. If it's a very elongated orbit, then probably this the current semi might be, or at some point, bigger than this. I'm not sure, but just make sure we don't get negative numbers. I'm not sure if what happens then, but you can't take the square root of a negative number. Should make no difference, but I'm open for suggestions in this case. So let's see, that's the same just for the transfer orbit, and first burn. Oh yeah, we're calculating the delta V. We don't care about the direction actually. We just want to know the difference. Who per speed minus per speed. So now we get our first burn, delta V, and that should be meters per second. So let's see, what did we call it? Nothing, because we forgot to change the names. Now we're gonna do it, it's called burn 1, HTML, just first burn, and you know what, we just round it, because yeah, that half a meter per second, more or less, you know. What's the difference anyway? It's more readable. If you want to be really exact, you might not program this with floating point arithmetic on the JavaScript anyway, so but it should give you a rough idea how much delta V you need. So let's reload, make it go, and that would be a bit much, actually. Let's see. Where did I go wrong? Of course. Let's see. Zack. No, this should be more reasonable. Hope. Make it go. We need a delta V burn for 2400 meters per second. Yeah. That doesn't sound completely wrong. Okay. Let's do something similar for the second burn. Let's see, what we need is the new periapsis speed, so that the periapsis speed of the final orbit, the new orbit, and we need to know how fast we are on the apoapsis of the transfer orbit. So okay, and the second burn is the apoapsis speed of the transfer orbit minus the new periapsis speed. We take an absolute, so we ignore the sign. Let's take a look. And we are not. Hello? Hello. Burn 2. We put it in burn 2. Oops. Whole up speed is not defined. Okay. Up speed. Let's see. Zack. Yes, 1468 meters per second also sounds somewhat reasonable. The total delta V is first burn plus second burn. Okay. Calculate total delta V, and we put this in total delta V. Okay, yes. Maybe, yeah, I should have guessed. So, which means this is total delta V we reload, make it go, and nothing. Yes, that's when you life hack sometimes. Yeah, which is of course diff element, so it needs val. Make it go. Total delta V required for orbit transfer 3896 meters per second, more or less. Okay, that's it. Thank you for watching. Goodbye.